back, grade 11s. I hope that the exponent law lesson went well for you and you're feeling good about some of those basic exponent laws. I hope you're ready to learn about something new. We're going to talk about what if an exponent was 0? Or what if the exponent was negative? Is that even possible? Well, hello there. Let's just take a look at that together, shall we?
So in our last lesson, we talked about the idea of an exponent or a power. We talked about the idea that 2 to the power of 4 is simply a shortcut for writing 2 times 2 times 2 times 2. Some students and teachers say 2 times itself 4 times. Have to be a little bit careful with that language because technically 2 times itself 4 times would mean you have 5 2's. We'll get into that in just a second. But first, we think of this as a shortcut. Even talked about some Greek mathematicians who decided that this is how they would write 2 times 2 times 2 as 2 to the power of 4. But then people started asking questions like this. Well, if that's what 2 to the power of 4 is, what about 2 to the power of 1? Well, we used that yesterday. It seems to make a lot of sense that 2 to the power of 1 should just be equal to 2. And of course it is. But other questions might be, what about 2 to the power of 0? Is that something? Should that be something? Does that even make sense? How about 2 to the power of negative 1? Or even 2 to the power of negative 3? Is there such a thing as negative exponents? And if so, what do they mean? And as it turns out, they do mean something, which is good because otherwise this will be a very short lesson. Let me try to use some patterns and try to show you how we can discover not only what 2 to the power of 1 and 2 to the power of 0 have to equal, but 2 to the power of any negative exponent as well. So I've got this little table that I've jotted down here. 2 to the power of 4 is 16, and you see I've drawn the 16 circles here. 2 to the power of 3 is 8, 2 times 2 times 2, and I've got 8 circles. 2 squared is 4, and I've drawn 4 circles. Now there's some patterns that you can see here. The first big one to notice is that every time the exponent goes up, I'm multiplying by another 2, and so my result doubles. So it would make a lot of sense if 2 to the power of 1 had a number where that was still true, and sure enough it does too. If you put a 2 in here, this idea of doubling each time is still satisfied. And sure enough, 2 to the power of 1 is equal to 2. Well, if I double each time I go down in the table, it means I'm cutting something or dividing by 2 as I go up, since that's the inverse operation. So we could also see this as a pattern too. Well, if I continue this pattern, I might think about what 2 to the power of 0 looks like. And this is where in class I usually ask somebody to raise their hand and take a guess what number, if we're doubling each time or dividing by 2 as we go backwards, what number fits this pattern? Of course, the only number is the number 1. Sorry, I should have drawn 2 circles here. And as it turns out, yes, 2 to the power of 0 is equal to 1 because the pattern holds. Now if I continue, notice my exponents are going down by 1 as I go up, or up by 1 as I go down. That means that the next one here would be 2 to the power of negative 1. Well, what number can I put in here that will allow this pattern of doubling each time to continue? Well, if you instead look at dividing by 2 each time, 1 divided by 2 would be 1/2, or half a circle. And that is, in fact, what 2 to the power of 1 is equal to. How about if we continue? What about 2 to the power of negative 2? What would that have to be equal to? Well, notice we're still doubling. A half doubled is 1. 1 doubled is 2. 2 doubled is 4. What do you double to get a half? Or what do you get when you divide a half by 2? You get a quarter. Now, I'm going to be hard-pressed to draw a quarter of a circle. Maybe something like that. I don't know. That's pretty terrible, but there you go. And I can continue. I could keep going if I want. How about 2 to the power of negative 3? Well, half of a quarter is an eighth. And sure enough, 2 to the power of negative 3 is in fact 1/8. So these numbers are exactly what allows this doubling pattern to continue going. Okay, the circles didn't work out as well as I hoped. I have a very hard time drawing them on here. But 1/8 of a circle doubled to give you 1/4 of a circle, doubled to give you 1/2 of a circle, doubled to give you 1, then 2, then 4, then 8, and 16. So from this table, the first lesson to be learned here is that 2 to the power of 0 is equal to 1. Now, it doesn't matter that I use 2 here. Had I used 3s or 4s or any other number, you would have saw the same type of pattern, and you would have found that no matter what your base was, anything to the power of 0 is equal to 1. The second lesson is notice each of these numbers up here. So I'm just looking up at the top right here again. Notice that I get 1/2 or 1 over 2 to the power of 1. And here I get 1/4 or 1 over 2 squared. And here I get 1/8 or 1 over 2 to the power of 3. So really, 2 to the power of negative n is 1 over 2 to the power of n. For example, 2 to the power of negative 3 was 1 over 2 cubed, which is 1/8. In general, I could do the same table for powers of 3 or powers of 4 or powers of 5 or whatever I want, and I get a very similar result, and that is that a to the power of negative n is always 1 over a to the power of n. That's a very important rule for today. So is this. Let's look at some simple examples. 7 to the power of 0, well, 7 to the power of 0 is equal to 1. 4 to the power of negative 3 is 1 over 4 to the power of 3, which is also 1 over 64. Now there's another way of looking at negative exponents. If this was 4 to the power of 3, you would multiply by 4 3 times. You can think of 4 to the power of negative 3 as kind of like, instead of multiplying by 4 3 times, you're dividing by 4 3 times. Now, notice how I said 4 to the power of 3 at the beginning of the lesson, and I said it's a little bit wrong to say 4 to the power of 3 is 4 times itself 3 times, because that would mean you have 4 4s, and there's only 3. So you actually could look at it as you're taking the number 1 and multiplying it by itself 4 times. And for 4 to the power of negative 3, you're taking the number 1 and you're dividing it by 4 3 times to give you 1 over 4 cubed, or 1 over 64. In fact, if we continue with that explanation, you could say that 4 to the power of 0 is the number 1 and don't do anything with it. Same with 7 to the power of 0. Take the number 7, don't do anything with it. Those rules about zero exponents and negative exponents allow something else interesting to happen. So remember yesterday we talked about dividing powers with the same base. For example, a base of 5 here. Well, imagine we had 5 to the power of 3 divided by 5 to the power of 3. If we went to use our exponent laws, we'd say that you need to subtract the exponents. Well, 3 minus 3 is 0, and we get 5 to the power of 0, which is an interesting result. Well, 5 to the power of 3 is 125. So really, 5 to the power of 3 divided by 5 to the power of 3 is 125 divided by 125, which is equal to 1. Hey, look at that. Isn't that super exciting? Like we said, 5 to the power of 0 is 1. Well, it better be 1, because 125 divided by 125 is definitely 1. So this allows our exponent laws to continue to work even when we subtract the exponents and get 0. How about the next one with powers of 3? So what we did yesterday, we'd say dealing with powers of 3, you can subtract the exponents when you divide. But in this case, it's kind of strange, because 3 minus 7 is negative 4. So if you'd done that question yesterday, you would have got, or whatever day it was, you would have got 3 to the power of negative 4. Well, another way to look at this example is that the numerator is really 3 times 3 times 3. The denominator is 7 3s. Let me just write those out quickly here. 3, 4, 5, 6, 7. So 7 3s. Well, how do I evaluate that? I could, if I wanted to, start dividing 3s. And on the numerator, I have 1, and then I have 1, 2, 3, 4 3s down here. So 1 over 3 to the power of 4. So I know that 3 to the power of 3 divided by 3 to the power of 7 is definitely 1 over 3/4. According to our exponent laws, though, it's 3 to the power of negative 4, and what we just learned is that that is the same as 1 over 3 to the power of 4. See, do you see how everybody is happy here? How the exponent laws work with our definition of negative exponents, the fact that 3 to the power of negative 4 equals 1 over 3 to the power of 4 is really convenient because it allows an expression like this to be calculated both using our exponent laws and without using our exponent laws. So I think that that's kind of interesting. What happens with negative exponents if our base is a fraction? So that's definitely, I mean, our rule for negative exponents was a to the power of negative n equals 1 over a to the n. So we can kind of apply that here, and we can say that 2/3 to the power of negative 2, technically now our a value is 2/3, so it's 1 over 2/3 squared. That doesn't look very pretty. We should never need fractions in fractions. So let's continue to look at this example and see what happens. Now, 2 squared over 3 squared is technically 1 over 2 squared over 3 squared. Now, I know that that's 4 over 9, but I'm just going to leave it like that for now. How do you handle a fraction in a fraction? Well, you treat the big fraction as if it's a division symbol. How do you divide fractions? Well, you multiply by the reciprocal. So this is like 1 over 1 times 3 squared over 2 squared. And multiplying by 1 is really easy. I just get 3 squared over 2 squared. So notice what happened to 2/3 to the power of negative 2. I ended up getting 3 squared over 2 squared. Or if I want, I could write that like this, 3 over 2 all squared. Now notice that if I were to redo this example, and I were to replace, say, my 2 with some other number, and my 3 with another number, and my negative 2 with another negative number, all the math would still be the same. I just end up with different numbers at the end. So in general, a over b to the power of negative n is the same as b over a to the positive n. After that, we usually use this rule here. Should kind of make sense too. Remember I said how negative exponents are kind of like dividing instead of multiplying? Well, if your base is a fraction, how do you divide fractions? You multiply by the reciprocal. So we trade the negative exponent in for the reciprocal. Flip the fraction upside down. So that kind of makes sense too. So in summary, here's what we learned. Anything to the power of 0 is equal to 1. If you have a negative exponent, okay, you treat it like that. For example, 3 to the power of negative 2 is 1 over 3 squared. And finally, if the base of your power is a fraction and you have a negative exponent, you can flip or take the reciprocal of that fraction. So for example, if I do one quickly, 2/9 to the power of negative 3 is 9/2 to the power of positive 3. So let's look at a few more examples. Now, it's important to notice that when we combine negative exponents with the material learned in the last lesson, our basic exponent laws, I highly recommend you use those basic exponent laws first. Today you're probably looking at this and you're tempted to take 5 to the negative 1 and change it to a fifth, and 5 to the power of negative 4 and change it to 1 over 5 to the power of 4. But a better idea instead is to actually add the exponents together because you're multiplying powers of 5. Negative 1 plus 3 is 2, and 2 plus negative 4 is negative 2. So this is the same as 5 to the power of negative 2, which is 1 over 5 squared. Okay, now 1 over 5 squared also happens to be 1 over 25, but really this is really the important part of this question. Okay, negative 1/3 to the power of negative 4. We can take the reciprocal of that. It doesn't really matter where the negative goes here. To the power of positive 4. Okay, now negative 3 to the power of positive 4, notice the 1, we don't need that anymore, it's just positive 81. And for the last example in this lesson, we have powers of x. Just like with the example I did in the last lesson, if you have a bunch of powers of x, you can always write that as a single power of x. So let's start with the power of a power. Being careful here, because 5 to the power of negative 1 is 5 times negative 1, which is negative 5. Sorry, my pen's not working very good here for some reason. That's x to the power of 1, all divided by x to the power of negative 3. Okay, looking at the numerator, I can add the exponents. 2 plus negative 5 is negative 3, plus 1 more gives me negative 2. So I have x to the power, sorry about that, hang on one second here, x to the power of negative 2 divided by x to the power of negative 3. Again, I don't want to change this into 1 over x squared and 1 over x cubed. It's better to use the basic exponent laws first, in this case dividing powers. Otherwise you introduce a whole bunch of fractions in one expression. Now I can subtract exponents, but be careful. This is negative 2 take away negative 3, which is technically negative 2 plus 3, which is 1. I get x to the power of 1 or just x. In fact, if I follow the basic exponent laws in this example, I don't even need to worry about dealing with negative exponents because there ends up not being any anyways. Okay, good luck with today's question. Please email me if you have any problems, and I'll see you next time.